Welcome to the Pathfinder's Codex, where we try fun things in computer programming, for both beginners and seasoned coders. Today we're going to cover the basics of 2D shaders in the Godot game engine. This is part 1 of a 4-part learning series, with each video walking you through several 2D practice shaders. We'll go through and pick apart each one to see what makes them tick. Now, these videos will only contain the simplest of shaders, and hopefully I've organized them in a way so that each practice shader helps you build a foundation for later videos. The original versions of these shaders can be found on GodotShaders.com. All credit for that original code goes to those creators and those that inspired them. However, I've simplified and compacted a bunch of the code to make it easier to learn from, so what you see today probably won't match up with the code that's on the website. Okay, let's get to it. First, let's look at the type of shader we're going to be using. We'll be working with Godot's canvas item material shaders that affect 2D textures and sprites in our projects. There are other types of shaders too, but we'll only focus on these 2D materials for this series. A canvas item material shader allows us to change an image or a texture on the screen using math and other cool techniques, pixel by pixel. At its core, it allows us to change any of the pixels in the original image or texture, and we can use any number of ways to determine how and what pixels to change. For most of these practice shaders, we'll use the Godot logo icon as the sprite texture. We'll sometimes use a second image, a pixel art mech suit, so we can play around with border detection and other neat effects like transparency. Let's see where they show up in the Godot editor. A shader is assigned to textures, canvases, and sprites within your game using a material resource. You'll usually find the material properties in the canvas items section in the inspector. Each material will need a shader script. That's where the instructions for the shader will live, and they'll have a .gd shader extension over here in the editor file system. We could also create materials or scripts once and reuse them on many different nodes. But for all of the shader examples we're covering today, each one will have its own material and a unique script file. Once the material resource and the script is attached to the node, we can open it and start writing the shader code. The code will appear in the shader editor down here. And since these shaders run in the editor, we won't need to restart the game to see the effects. Pretty cool, huh? If you find these practice shaders useful, be sure to subscribe and leave a comment to let me know you want more of this type of content. Alright, let's jump into our first shader. This one's called Color Channel Red, and as the name suggests, it's all about changing the red color channel of an input texture. It's a good place to start because it introduces us to the most basic elements of shader programming. The fragment coordinate and UV system, how to access the source texture, how to manipulate the output colors, and using uniform variables to control different input parameters into the shader. Here's how the code works. The shader type canvas item line tells Godot that this shader will be used on 2D textures or sprites. All of our practice shaders will use this mode. Then we define a uniform variable called red. Uniforms are handy because they let us set parameters directly in the Godot editor, or through scripts, without changing the shader code itself. It's great because we can see them over here in the inspector, change the values here, and then see the results in real time in our scene. In this case, the red variable controls how much red is included in the texture, with the default value of 1. We can change it down to 0 and we instantly see the effect on our logo. Shaders later in this series will have a bunch of input parameters here, with all sorts of controls and purposes. Next, we have the fragment function. This is an important built-in function that runs for each pixel of the texture, allowing us to modify the image's appearance. For the first line, we grab the color of the logo using the texture function, and make it the default output color for this fragment. Now, there's a lot packed into that one line, so let's take a look at it step by step. First off, the special texture variable. This built-in variable is the actual image or texture that the shader is working on. It could be a sprite's image, a tile map texture, or pretty much anything we've applied the shader to. Think of it as the raw source that we're about to read from. In this first shader, it's the Godot logo image. Then there's the built-in UV variable. This is how we figure out which color of the texture we're looking at for the current pixel. Remember we said that this fragment function runs for each pixel? Well, our fragment function doesn't actually know anything about pixels. It only knows how to use a fragment coordinate to tell us which color it's working on, which is conveniently stored in the UV variable. Throughout these videos, I might refer to them as pixels, but that's not exactly accurate. They're fragments, and the UV is the color information for the current fragment we're working on. You can think of UV and fragment coordinates as kind of a grid map of the texture. They start at 0, 0 in the top left of the texture and go all the way to 1, 1 in the bottom right corner. The y-axis can sometimes be flipped depending on the engine you're using, so be aware of that if you ever see your results turned upside down. These coordinates are normalized, which means they're based on a percentage of the texture rather than the actual pixel dimensions. So whether your texture is 100 pixels wide or 1,000 pixels wide, the UV will always work the same way and will always go from 0 to 1 on both axes. Now, when we combine these two variables with the texture function, what we're doing is sampling the pixel from the logo at the current fragment UV coordinates and reading that color. This gives us the pixel's original color, which will be a vector 4 variable. That's just a fancy way of saying that it's made up of 4 individual parts. R for red, G for green, B for blue, and A for alpha, which is the transparency. We'll use vector 4 for many colors, but sometimes we'll ignore the alpha transparency and just use a vector 3 instead. These vector formats are commonly referred to as the RGB color format, and they're used all over in video, graphics, and shaders. So the last thing the code does is assign that vector 4 RGB color to this color variable. This is another special built-in variable in a fragment function. It's where we'll set the output color for the current fragment, and it's how we'll change the final image. Whatever value we assign into this color variable is what the fragment will show on the screen. Now that we've got the original pixel color and made it our default output color for the pixel, we can start making changes to it. Here's the cool part. You can change each of the color channels individually in a vector 4. So in this shader, we're only messing with the red output channel, which is color.r. But you could do this with any of the channels like color.g or color.b. We take the input from our red uniform and put that directly into color.r. The other parts of the color, like green and blue, won't be changed, and they'll look just like the original image. This means that instead of the red intensity from the original texture, we're replacing it with whatever value we sent in as the red uniform. If the red uniform is set to 1, then the red channel is fully saturated. It'll be at max intensity. If it's set to 0, then the red channel will be completely turned off. And if it's somewhere in between like 0.5, it will get a softer red. This range, where a variable only goes from 0 to 1, is common in math and shaders, and we call it a normalized or continuous value. We'll look at mapping values using interpolation and normalization in later shaders. So in just a couple of lines, this shader gives us complete control over the red channel of our texture, while leaving the green, blue, and alpha channels completely untouched. It's super simple, and it's a perfect starting point to see how shaders let you manipulate textures on a pixel-by-pixel basis. Still with me? Alright, now that we've got the basics with our first shader, let's move on to something a little bit more advanced, but still beginner-friendly. This one's called Replace Color, and it's all about swapping out one color in your texture for another, using some creative tricks. In this second shader, we'll use the mech suit texture instead of the Godot logo. This shader introduces a couple of new concepts, but don't worry, we'll break it all down step by step. Here's how it works. First, we start with the same line as before. This tells Godot we're working with a 2D texture or sprite. No surprises there. But this time we'll have 3 uniforms that we can control for inputs. It has the color to be replaced, a threshold to control how close a color needs to be for it to be replaced, and the color to replace it with, which we'll call the mask. Like before, we see these parameters in the Godot editor when viewing the material. But unlike before, 2 of these parameters are not just basic numbers. The color to be replaced and the mask color are vector 3s. Notice in the editor the 3 parts show up as X, Y, and Z, but we'll treat those as R, G, and B channels to represent a color. Colors in Godot are stored using 0 to 255 for each channel, instead of the normalized values between 0 and 1. We'll see in a moment why that's important and how we're going to deal with it. Before we check out the fragment function, I wanted to mention something else about these shader uniforms. Not only can we change these parameters in the editor to see the effects in real time, but we can also use these variables in our code and scripts. Here's how it would work with the first 2 shaders in our series. Here we can set the red channel we saw in our first shader directly in code. And in the Replace Color shader we're talking about now, we can set both the mask or color to be replaced in the same way, using Godot's color constants. This makes things simpler to read and allows us to create one shader to do a lot of different things, even animate and tween the values. Okay, back to the shader code and our fragment function. In the first shader, we saw how this function runs for all pixels in the texture, and it used the UV color details for each pixel. We'll do the same here. First thing we'll do is make the default output color the same as the input color from our mech sprite. But here's where we're going to change it up. This shader has two decisions to make. First, how does it know if it should replace the current color with the mask? And second, what color does it actually use for that mask if a color needs to be replaced? Let's answer those in reverse. In our first shader, we saw how to change just the red channel of the vector4 color variable. This time we're going to change 3 channels at once, red, green, and blue channels. Assuming we want to replace the color, this line of code takes our color stored in the mask uniform, normalizes it, and sets the result as our output color. The mask variable stores a color channel using values between 0 and 255, because that's the standard way colors are represented in Godot's color class. But in shaders, we typically work with values between 0 and 1. So to convert the mask color into a format we can use, we divide each of its red, green, and blue components by 255. This normalization scales each of the values so that they'll be in a range between 0 and 1, making them compatible with our shader calculations. Notice that we're only changing the RGB channels here. The alpha channel, which controls transparency, remains untouched. This means if the original texture had a transparent area, it'll still be transparent after the color swap. Vector math can be complicated, and while we'll see a lot of it in the shaders throughout this series, we won't be covering the theory in detail. Instead, we'll focus on practical applications like this one, where simple division helps us work with colors in a way that makes sense for shaders. Now let's go back to the first question. How does the shader decide if it should leave the original color from the input texture, or if it should use the mask color? What this if condition is looking for is the distance between our current fragment color and the color to be replaced, and if that distance is within our threshold. Earlier, we used color.r to access just the red channel, a single number between 0 and 1. Here, color.rgb represents the entire color as a vector3 containing red, green, and blue components together. To decide to replace a color, we need to compare two colors. Color.rgb is the current color of the fragment taken directly from the input texture. Since shaders expect colors to be between 0 and 1, we also divide this vector variable by 255, just like we did with the mask color earlier. This ensures that both colors are in the same 0 to 1 range before we compare them. This conversion process is something you'll see often when working with colors and shaders, especially when dealing with values that come from external sources like Godot's color class. Once we have the two normalized colors, both ranging from 0 to 1 in each channel, we'll pass them into the distance function. This function measures the distance between two colors, but what does distance mean here? Simply put, it's the straight line measurement between 2 points in either a 2D or a 3D space. Think of it as drawing a ruler between any 2 points in a square or a cube. And since these colors are 3-part vectors, and they're normalized between 0 and 1, they can be represented as a 3D cube. This allows us to use the distance function to say how close are these two colors inside the cube. So now we know how far apart our original fragment color is from the color that we want to replace. We compare that distance to our threshold uniform. The threshold is how short the ruler needs to be to trigger the color swap. If the distance is smaller than this value, we trigger the color swap. A low threshold makes the condition stricter, meaning colors must be very similar, while a higher value here allows us for greater variation with more colors being replaced by the mask. If we only want to replace an exact color, we would set the threshold to 0. Like before, you can play around and change these shader parameters to instantly see the effects while you're in the editor. We'll take that a step further in the next shader by using uniform hints. And like we talked about earlier, you can even change uniform settings using code to animate or interpolate these inputs over time, or in response to different events in your game. Okay, let's keep going with shader number 3. Now let's bump it up a little and use the HSV color model. We'll control the hue and saturation of a color instead of using RGB colors. We'll create a rainbow type effect in our image and call it a radial hue shader. This shader will have one uniform, called influence, that lets us control how much of the new color is blended into the original texture. This influence represents the amount of color blending to use, and it ranges from 0, or having no effect, to 1, having full effect. This is the first time that we're seeing a hint range for a uniform. The hint range here makes it really user-friendly by allowing us to adjust the parameters in the Godot editor using a slider control. There are other great hint features that you can check out to make it even more useful, and we'll see some of those in future shaders. Now let's talk about the first of the two functions in the shader, the HSV to RGB function. This function will convert an input color from an HSV value to its corresponding RGB value. But why do we need to do this? Well, HSV is super handy when you want to work with colors in a way that feels more natural, like you might see in a color wheel or in a rainbow. Chances are you've seen this format in color pickers in many different tools and applications. Instead of thinking about how much red, green, or blue a color has, the HSV lets us think of colors in a more natural way. The color itself is called the hue, and we'll represent it as an angle on a color wheel. In this shader, we normalize the hue to a value between 0 and 1, where both 0 and 1 represent the same hue and all available colors are spread across that space between 0 and 1. The saturation is how vivid the color will be, with 1 being fully saturated and 0 being white or completely unsaturated. And the value is how bright or dark the color is, where 1 is the brightest and 0 is completely black. Using HSV allows us to better control gradients and moving around within the color space, and not have to worry about exactly how much red or green or blue goes into whatever color we're working with. But then computer displays really don't understand HSV. They use RGB when they show pixels, so this function will help us convert any HSV color we have into their matching RGB color. In later shaders, we're going to see the reverse of this function, where it converts the RGB format back into an HSV, but we won't need that for today. Okay, let's shift gears and look at the fragment function, where we'll use the HSV conversion to change our fragment output colors. The first step is to adjust our coordinate system. This is important because our radial hue effect is all about the relationship between our current pixel and the center of the image. Luckily, the data in the UV variable wraps around itself, essentially repeating the data in all directions. So by subtracting our current UV value from vector 2.5, we'll always be comparing our current pixel to the center of the texture instead of the top left corner. Once we have this adjusted position, we can figure out the hue by using the arctan function, which gives us an angle of the current pixel relative to that center pixel. That angle becomes our hue value, which smoothly wraps around the texture to create a continuous spectrum of repeating colors. Next, we'll calculate the saturation by taking the length of our position vector and multiplying it by 3 to make it more pronounced. In simple terms, the further away a pixel is from the center, the more saturated the color will become. And we'll leave the value component fixed at 1, ensuring that our colors stay bright and vibrant, but we can just as easily change this value if we wanted to. Finally, we pass the 3 parts, the H, the S, and the V, into our HSV conversion function, which gives us back the RGB color that our shader can use. We then blend this new color with the original fragment color from the texture by multiplying it by our influence uniform. Think of influence as a dial that controls how much of the new effect will be added to the original image. A value of 0 means no change, while 1 means 100% application. The actual blending here is simply done by adding our new dynamic color on top of the existing texture color, using the plus equals assignment notation. We could do this with a simple equals assignment, but then we'd lose the original image color and only see the radial hue introduced by our shader. And that's the breakdown. With this shader, we're taking advantage of some clever math to map each pixel's position into a beautiful rainbow-like overlay. The closer a pixel is to the center, the less vivid its color shift, and the further out, the stronger the effect. We can control the amount of color merging using our influence uniform, either in the editor or even in code, to make some interesting animations or sequences. It's a great example of how shaders can combine with math, color theory, and creativity to produce something visually appealing. First up is a shader that introduces the time feature to animate our output results. The Radial Rotate shader. In this one, we're going to modify the texture with a spinning pattern of colors that rotates over time. The shader only has one input, and it allows us to control the speed of the spinning effect. Setting the speed to 0 will stop the spin, setting it higher will increase the speed, and setting it negative will actually reverse the direction. Let's figure out how it works. First, we'll look at this built-in time variable. This time variable is a special built-in value that tells the shader how much time has passed since the shader has first started running. And by combining it with our speed uniform, we can use this to animate parts of the shader logic at any speed we want. We'll store this adjusted time in the variable t so we can use it later. Before we apply our motion, let's look at another common concept found in these shaders: the scaling of the UV and fragment coordinate system. In the first episode, we learned how to center ourselves in the UV space by subtracting the UV position from vector 2, 0.5, and we're going to do the same here. This lets us create our effect at the center of the image instead of at the top left, and you can see what happens if we were to temporarily remove that part of the code. So now that we're centered, we're also going to multiply that result by vector 2, 2.0. This is how we'll scale and zoom the shader in and out. You can do some interesting things with this type of scaling, and we'll see more of it in future shaders, but for now we're just going to keep it simple. This scales the entire UV space by a factor of 2, which will make our output appear zoomed out and smaller than it's actually supposed to be. You can see the effect this has on the output. For example, if we were to remove the scaling completely, then our rotating effect will get larger. On the other hand, if we have the values, by multiplying by vector 2, 0.5, the effect would be even larger. Great! Now we have the adjusted position of our pixel, centered and scaled the way we want it. We'll use this position to find the distance from, and the angle compared to, the center of the image. In the last episode, we used the same functions, and you can refer back to that video if you would need a refresher. Now comes the fun stuff. Let's create the color output for the current pixel. We'll do that by treating each color channel, the red, green, and blue, in slightly different ways and at different speeds. First, notice that we're including the speed factor here, the variable t, in each of the channels. Then, each channel also has its own multiplier, so in this case, the blue channel will be moving slowest with a multiplier of 15, and the green channel will be the fastest with a multiplier of 5. By passing our angle and our customizable speed factor into the sine and cosine wave functions, we'll get the channel values that are not only based on their locations, but also based on their time that the shader's been running. And because we're using the sine and cosine functions, we're also getting movement that's periodic and oscillating back and forth. While it's not critical for this shader, we'll also cut the colors in half by adding 1 and multiplying by 0.5. In fact, you can change any of these values to fit your needs to try different variations. For example, if you really want to make the green channel pop out, you could remove the halving value. Or if you wanted the blue channel to spin really fast, you could change the 15 down to a 1, or even make it negative to change the direction of that channel. You can even take this to the extreme and remove any of the channels with a value of 0, and it might give you a better sense of what's going on with the other channels. Feel free to explore and try different values here. Next is another optional line of code. By using our pixel's distance from the center point, we can get a soft fade out as the pixels get further away from that center. We'll use the smooth step function along with the distance value and multiply the results into our color. Like before, we can remove this line of code to see what the impact is. The last line of code is where we assign our dynamic color into the output color. This should be familiar as it's how we've assigned output colors in the first episode. The only difference here is we're going to make the alpha transparency from the input texture and use that in the output texture. Basically, if the original texture had transparency at any given pixel, that transparency will also be applied in our output image. One last comment here. We're doing a full overwrite of the output image by using the equals assignment operator. This means we completely lose the original image texture in our output. Recalling back to the first episode, if we want to add our new effect on top of the input image, we would use the plus equals assignment operator, like this. Our radial rotate shader is looking pretty good, and we can now use the time feature in our shader to make some interesting time-based animations. Next, let's move on to a shader that skews and stretches our original image using the powerful vertex function. The Shadow Effect Shader. For this practice shader, we're switching things up by working with a pixel art mech sprite that has a bunch of transparent pixels. It only contains a single input uniform, a flag that lets us control whether the shadow should be flipped left or right. And since our mech suit is facing right by default, we'll use the look right option for this. In previous shaders, we've been using the built-in fragment function to change the color of pixels. Next, we'll introduce the vertex shader function. We'll not only change the colors in the fragment stage, we'll also manipulate the geometry of the image first in the vertex stage. In Godot, the vertex stage runs once per quad corner, before any pixel shading, giving us full control over the image shape. We can stretch, squash, skew, and even flip our texture using this function. A vertex is a point. Shapes with 4 points are generally called quads and sometimes rectangles. And since our sprites and textures are always rectangles, there will always be 4 points that represent the corners of the image. The vertex function actually supports more than 4 vertices, and there can be as little as 1 vertex in some cases. But for most of the 2D shaders we're working on, there's always going to be 4 corners to work with. The function runs once for each of the 4 corners. Okay, let's jump into the vertex function. Here's how we use it in this shader. First, we flip our mech's horizontal alignment based on the look right uniform. The vertex variable here is a special built-in variable that serves 2 purposes. It holds the original x and y coordinates for the corner being worked on, and it's also how we'll change those coordinates. We can feed any vector we want into this vertex variable, and the image on the screen will be adjusted accordingly. Notice how multiplying vertex.x by either -1 or 1, using this little array lookup, instantly mirrors the image when we toggle the flag on and off. Mirroring, check. Next, we can squash the shape. We'll do this by pushing the bottom 2 points up to the x-axis. To figure out if a point is one of the bottom 2, we'll check if its y component is negative. If it is, we'll move its y component up to 0. We completely overwrite the point's coordinates into the vertex variable to save this change. After all vertices are processed, the shape changes from its original rectangle into a half rectangle, where the bottom edge has been squashed into the x-axis. Squashing, check. As the last step, let's skew the shape to give it some perspective. We'll do this by pushing the top 2 points outward, based on how far they are from the center. First, we'll check if the point belongs to the top half, by seeing if its uv.y value is greater than or equal to 0.5. If it is, we calculate how much to move it by using the absolute value of its x-coordinate. Points farther away from the center move more, while points near the center move less. We then add this horizontal shift to our working vertex coordinates to save the change. This applies the skew to our already squashed quad. After all vertices are processed, this stretches the top half of the rectangle outward, turning the shape into a trapezoid. Skewing, check. So as you can see in the preview, these combined operations reshape the quad into a skewed box, and the texture inside the box will be skewed to match our new corners. With the geometry now reshaped, we're all set to move into the fragment stage and fill it in with a silhouette. We'll replace the original texture entirely with a shadow color that respects the transparency of the original image. The color for the shadow will be constant, but you can see what happens if we were to use a plus equals assignment operator here, instead of the raw assignment operator. The shadow would then get the same colors as the original sprite. That's not the effect that we want, so we'll stick with the assignment operator. The only problem now is that we've completely lost the original mech suit image, because we've manipulated the vertex corners. Let's fix that. To add the original image back into the picture, we're going to cheat a little, and add a second sprite node. This is the first shader where we're going to use a second sprite to get the full effect. We'll simply nest this new sprite inside the existing one, so it shows on top of our shadow. And we'll give this new sprite the same size and texture as the first. Only this time we won't give it our shader material. Awesome, we now have a shadow effect appearing underneath our original unskewed sprite. And we can view the shadow with or without the original texture by hiding the new sprite node. We'll use this same two-sprite technique in the next shader. So let's check out the last shader for today, where we're going to surround a rectangular texture with a moving border. The Animated Border Shader, version 1. In this shader, we're applying an animated outline effect that looks like a moving dashed border. It has a bunch of input settings to control the look and feel. We've got one for the direction of the animation, one for the frequency of the dashes, another for the speed of the dashes, the overall radius of a circle, the thickness of the line, and the color of the border. When we get to the code, we'll see how each of these come together to create the animated border effect. Like the last shader, this one relies on two different sprites, one nested within the other. The main difference this time is that the second sprite will use a z-index of -1. This makes the shader effect show on top of the image instead of behind it. We'll re-enable that second sprite at the end after we've walked through the shader code. Let's start by introducing a new uniform hint for us to use. By using the source color uniform hint, we can choose a color directly from the inspector's color picker, instead of having to set the individual values for the 4 channels every time. It's a nice quality of life feature for sure. Okay, let's jump into the fragment function and break it down on screen. First, we center our UV like we've done several times before. Next, we'll create a circle by measuring the distance to our center position. We'll use the step function to decide if a pixel is inside our desired radius. Let's remove all of the other logic out of this shader just for a second. Then it'll be easier to visualize what this circle is doing. Okay, now let's lower the radius down to 0.5, and even further down, or back up. I usually keep this at a max radius of 1, just to make sure that the pattern extends beyond all parts of the texture. I'll crank it back up in a second. The next part of the code applies animation to our circle. We've used the arctan function in earlier shaders to get the angle relative to the center position. We'll do that here just like before. Next, we'll create a wavy animated effect that moves around the circle. We'll use our recently discussed time variable and a few of our input parameters, and pass those into the sine function to create a sine wave pattern. It looks like this. We'll also make the arms in the circle more distinct by using the step function, which gives us this. Now we're getting somewhere. We'll store this rotating pattern in a new variable, because we'll need it in a second. As we're doing that, we need to make sure it uses the same alpha transparency that was sent in for the border color. It might not seem important, but this is required if we want to create partially transparent borders. Okay, let's push the radius back up so our pattern covers the entire texture again. So far so good. Our animated border is going to hug the inside of the texture edges, so what we want to do is create a mask. The mask will check if a pixel is near the edge of a texture, specifically if it's within our desired line thickness uniform. To bring it all together, we combine the circle with the mask. We can multiply the rotating pattern we stored above with this border mask, acting as the new transparency channel. If the pixel is too close to the center, the mask should erase it out, keeping only the pixels that sit close enough to the border. So now we can finally re-enable that second sprite holding the original image, and make sure it shows up behind our new border effect. And mission accomplished. It looks great, and we have a ton of customization options with all these input parameters. First up is a warm-up shader, the Shifting Hue Gradient shader. This shader lets you control the strength, speed, and angle of the color shifting effect. Let's build it from the ground up. First, let's split the texture into 2 parts, left and right, and set it up so we can rotate it around the center of the texture. We're converting our input angle to radians here because Godot is sending in degrees between 0 and 360. That'll give us the rotation effect. And we're centering the UV by subtracting vector 2, 0.5 like we did in many of the other shaders we've seen so far. Then, we'll decide the output color. It'll be grayscale for now, and it'll wrap between 0 and 1 starting at the center of the image. We'll use the fract function to ensure we have a loop. This function returns the decimal part of a floating point number, which is how we'll create the looping values that are always between 0 and 1. We can test the rotation logic by changing the angle uniform to make sure it's working. Okay, now that we have the rotation and looping color, let's add the animation by using the time variable we learned about in the last video. and we'll make it configurable using an input speed uniform. We can change the speed of the color movement using this input. Nice, now we have both the animation and the rotation logic in place. Let's add the colors. Right now we have the color set to a single looping color band, from black to white, from 0 to 1. First, we'll break that value into 6 RGB color segments. The colors are broken down into 6 segments, where each segment represents a gradient from one color to the next. Why are we doing it this way instead of using the awesome HSV to RGB function that we learned about in episode 1? Well, it's easier for artists and developers to understand and tweak specific color ranges when using the if statements instead of a hard-coded formula. The end result is the same. We converted some hue bands to RGB, but now we can make further adjustments to any of the segments depending on the art style of the game or the needs of the graphics artist. Now, to finish up the shader, we'll finalize the image by mixing in the new color with the original texture's color. And we'll control exactly how much blending using a strength input variable. A strength of 1 fully overwrites the original image, while a 0 completely hides the new color effect. And there we go. We have some basic input controls, and we can use the shader for some simple effects in our games with just these options. And we could even expand the code that creates the 6 bands for even more control if we don't want the generic rainbow pattern. Great. Let's move on to the next shader where we can create some neat rotating marbles. The Wave Rotate Blur shader. This one's hard to describe. We're not really introducing new concepts here, we're just combining ideas we already talked about in different ways. And in this shader, we're completely overwriting the original texture, so it doesn't really matter what sprite we put it on because we won't see that sprite. The end result is a customizable image that resembles a fuzzy glass marble, where we can control different parts of the patterns on the rotating disc. Probably easier just to show you the nuts and bolts. First, we're going to make a temporary circle. We'll set up a distance-based fade-out and allow the developer to change the size of that circle using the scale uniform. This gives us the fuzzy circle mask, that we can make bigger or smaller using UV scaling. We'll apply that scaling zoom using square root to make the adjustments more gradual. And of course, it's centered in the UV space like many of the other shaders we've worked on. Okay, to make the rest of the shader easier to understand, I'm going to turn off this scaling and the fuzzy ball, and we'll come back to them in a second. Next, let's create a sine wave pattern and animate it. Nothing new here, and we've seen these concepts in previous shaders even if not in this exact setup. Here, we're rotating the entire wave pattern around the center point, and we can change the speed of the rotation using the speed input uniform. Okay, now we'll add 2 source color pickers, and have the sine waves use those colors instead of always using black and white. We can pick whatever colors we want, and they'll blend seamlessly from one hue to the other. I've also added some new input uniforms, so we can control different parts of the wave and rotate animation. We'll touch on those in a second. Perfect. With the color blending and the rotation working, we can bring back that fuzzy circle. We'll blend it in as transparency on top of our rotating waves. The end result is a spiraling circle that has the appearance of having an atmosphere. We also added more input uniforms. Each of these control different aspects of the rotation and motion of the effect. With those input settings in place, we can make the sine wave move, not just rotate. We can control the offsets of the animation and the rotation. We can decide how many waves it has with the frequency setting. And we can adjust the intensity of the blurring effect using a contrast input. I played with this shader a bunch and found that it makes some interesting marbles or pips that might look good in game interfaces. It could definitely be useful for procedurally generated textures. Here are some of my favorites as I was playing with the different uniform settings. Let me know what else you think this Godot-like pattern might be useful for. The next shader takes a concept we learned in the last video for making an animated border, and applies it to the sprite's pixels instead of the bounding rectangle around the texture. Let's check out Animated Border version 2 and do some basic edge detection. This one's great for highlighting selected items, adding glowing borders to your sprites, or emphasizing interactions in UI elements like menu items. Let's walk through it. First, we'll capture the alpha transparency from the original image. This gives us the transparent parts appearing black and the opaque parts appearing white. It's a grayscale mask showing where the sprite's pixels are. Next, we'll increase the size of the shape by detecting the edges and padding it with extra pixels. We'll use the built-in texture pixel size variable, combine it with our line thickness uniform, and use that to grow the shape in each of the cardinal directions by a certain number of pixels. That special texture pixel size variable gives us the exact size of one pixel in UV space. So when we combine it with line thickness, we'll be working with a true pixel size, which is useful especially when we're working with pixel-perfect effects. Here's how the outline logic works. Picture every pixel in your sprite as a little square on a grid. For the pixel the shader is currently drawing, we peek at its 4 closest neighbors, one step left, right, up, and down. We do that by nudging the UV coordinates in all 4 directions, where size is exactly 1 real pixel thanks to texture pixel size. The code determines how solid each of the neighbors are, where 1 is completely opaque and 0 is completely transparent. When we add up all of those alpha channels, we'll get an outline total. What does this running total mean? If all 4 neighbors are transparent, then the total will be 0, and we know this pixel is out in empty space. If at least one neighbor is opaque, even a little, then the sum will be more than 0, and we know we're touching one of the sprite's pixels or edges. To make things more crisp, we use the step function like a light switch. This way, we won't have to worry about partially transparent pixels, and we can just assume that any given pixel is either fully on or fully off. And if we wanted to, instead of using the step function, we could also do this with a rounding function. Our outline shape is now a clean black or white mask. In short, the shader sniffed the pixels' immediate neighbors. If any of them were solid, we marked the current pixel as part of the outline. So now we have a mask that includes a thin outline around our shape, and we can control the line thickness. We only used 4 cardinal directions when we sampled the texture UVs, which works in most cases, but let's make it more robust by including additional samples. The transparency check logic will be the same as before, but now we're sampling 12 points instead of 4. We'll include the diagonal pixels and even check some half pixels for finer control. This creates a fuller, rounder, and smoother outline. Now let's break down the texture into 3 distinct areas. To do that, we need to check a few things. First, we'll check the original texture's transparency. If we're less than half transparent, we'll assume the pixel is from the original image. If we're not inside the original sprite, maybe we're on the border. To check that, we can use the outline total we just created. If the outline value calculated is more than 0.5, we'll assume this pixel is part of the border shape, and we'll color that red. And finally, if the pixel is neither part of the original texture and it's not part of the shape area, we'll assume it's a transparent pixel. For now, I've made this last area white so we can see the 3 distinct areas. But when we finally change that to be transparent, we'll see the border that we want around our image and all the transparency is accounted for. Making progress step by step. Okay, now let's add the animation effect. To do that, we'll use the same technique we used in prior shaders to create a rotating set of arms in a circular pattern. To make it easier to visualize, let's hide the original texture pixels for a moment. Okay, now we can add the time-based animation. First, we'll add a few input parameters to control the color, the frequency, and the speed of the animation. Then in the fragment function, we'll use the arctan function to get our pixel's angle from the center to create the arms, and use the time and speed variables to make them rotate like we did in previous shaders. This adds a radar-like rotation to the area covered by the outline variable. It changed from red to white because now we're using the line color input setting, but otherwise this is our rotating circle infused onto our border shape. Neat. And now we just need to re-enable the original sprite's pixels to see the finished results. Looks good. We can choose our border color, speed up or slow down the rotation, change the line thickness, and control how many dashes we want using all of these different input parameters. There are a ton of ways to detect borders, some better than others depending on your needs. But this is one of the easier ways, especially if you don't need complex logic. Let's make another border effect, this time using noise to generate a flickery, almost fire-like effect around our texture. The last shader for today is Flicker Border. This shader is perfect for some pretty common effects like energy fields, magic sigils, or fiery sprites. It uses polar sampling for edge detection to create a flickering border around the pixels of the texture. We'll use some procedurally generated noise to create randomized but smooth variations in the effect. We'll start with the polar sampling and the edge detection, and gradually layer on time-based flicker and procedural noise, until we land on the final dynamic outline that you see here. Here's the gist. First, we need to know where the texture's pixels are. We'll sample the alpha channel at the current pixel UV. Anything below about 0.1 we'll treat as empty space, and we'll tint it bright red. Everything else will pass straight through. This quick pass gives us a mask of the silhouette and confirms our threshold is catching the transparent pixels. Next, we detect edges by sampling around each pixel in a tiny circle. This polar sampling will check if the current pixel is next to any non-transparent pixels. We'll need to add some constants for the shader. This angle res constant is how many samples we'll take as we move around the circle. So there will be 16 rays over the 360 degrees. In the fragment function, we're going to use the special texture pixel size variable again, like in the last shader. This way we can always be sure that we're jumping outward full pixels in every direction. Now we'll loop over the circle, once for each ray. Each ray adds the alpha it finds. If the sum is greater than 0, but our current pixel is still transparent, we know we're on a perimeter. And we're making it bright green to prove it's working. Looks like a border to me. A static outline is fine, but a flicker will bring it to life. First, let's add a frequency uniform so we can control the input. Good. And here, the time variable counts up each frame, multiplied by the frequency input, and flooring it to get discrete beats or pulses. We modulate the circle's radius with a small sine wave every beat to make it oscillate back and forth. The result is the tremble you see here in the now yellow border that pulses over time, perfect for things like sci-fi energy shields or item selection highlights. But let's take it a step further and rough up that border by making it noisy. We'll do that with some new input uniforms and a tiny pair of helper functions, hash and noise. The hash function will give us a repeatable pseudo-random value for any 2D point on the grid and any seed we give it. The noise function then uses 4 of those hash values and mixes them together. So instead of hard jumps, we'll get smooth hills and valleys, which gives us a more natural noise feel. And to use those 2 helper routines, we'll add one more function. The getLineWidth function blends together 3 layers of noise, called octaves, each adding finer detail at lower intensity. It scales the sampling location using a customizable block size. In this case, that means that every 3/4 pixel square shares a value, giving us chunky but interconnected details between the actual pixels. The value is then mapped between our desired minimum and maximum line widths, to give the border its organic uneven motion. This can result in positive or negative widths, where positive line widths will push our sampling circle outward, while negative widths will pull it inward. To bring it all together, we'll use these new functions in our fragment logic. And we'll add a color picker for the developer to choose the border color. The shader does 4 quick moves during each frame. First, the beat sync. It grabs the time step, which is our integer frame counter ticking at our desired beats per second. Second, the noise scale. It uses texture pixel size and getLineWidth, so every pixel decides exactly how far its 16 radial samples should reach out. We feed the current pixel's UV position into that line width function as the first parameter. And for the seed, we pass in that time step. So the noise changes once per flicker beat, not every frame. That keeps the noise motion smooth and stable without any harsh or jarring changes from frame to frame. Third, the polar scan. It marches around the circle for each ray, looking for opaque neighbors at the scaled offsets. And fourth, the painting. If we're sitting in an empty space but any neighbor is solid, we'll use the outline color uniform. Otherwise, we render the original sprite pixel untouched. The result is a border that flickers, crawls, and never quite repeats, ideal for magic sigils, crackling force fields, and your fiery sprites that need a bit of chaotic life. The outline now breathes, swelling, shrinking, and wriggling like living energy, and we can adjust the effect with any of the various input uniforms. Looks great, and it's a powerful introduction to using noise in a shader. This type of noise is known as value noise. There are lots of kinds of noise, and they have lots of different uses in game development. In future videos, I might spend some time going over noise in more detail and some of the cool things that you can do with it. And that's the flicker border shader. If you've followed along in our first 3 videos, you already know the basics of scaling UVs, working with fragment colors, moving corners and vertex functions, and even adding procedural noise and time-based animations. But today we're going to stack all the stuff we've learned in the series, plus learn a few new techniques like swizzling, mip-maps, and fake lighting, and even drawing effects outside of a sprite's original bounds. We're going to see a bunch of vector math in this code, but we won't focus on it too much, and instead I'll try to do my best to help you visualize how the working parts come together to create the final effects. These aren't just little shader snippets, they're full-on mini effects that you can drop in and customize for your own projects. Ghosts, blobs, portals, and waves. Let's get to it. Alright, first up is the Ghost Effect shader, and this time we're adding some custom enhancements to the original shader found on GodotShaders.com. The goal here is to make a sprite drift up to the sky and fade out like a ghost, but with an extra twist. We want the effect to render outside of the original rectangle bounds of the sprite. By default, fragment shaders only render within a sprite's mesh rectangle. That means shader effects can't extend beyond the sprite's borders. Common workarounds involve layering a second sprite, or even using particle shaders for more control. But this shader uses a more direct method, modifying the mesh in the vertex function. The mesh's corners are pushed outward by scaling the vertex positions, doubling them in this case. This expands the rectangle from a 0 to 1 range to a 0 to 2 range, giving the fragment shader more visual space to work with. However, scaling the mesh creates a new problem, UV distortion. The UV coordinates remain tied to the original 0 to 1 range, so the texture appears stretched out across the larger mesh. To correct this, the shader rescales the UVs in the fragment function. It recenters them by subtracting 0.5, scaling the results by 2, and then adding 0.5 back. This remaps the texture to fit cleanly and centered within the expanded space, preserving the original image while still allowing extra space around it for effects. Next, color swizzling is used to shift and remap colors and vector channels. Swizzling is a common technique, and we've already used it in previous shaders, we just didn't have a name for it. In this shader, the RGB components of the main texture are swizzled. Green becomes red, blue becomes green, and red becomes blue. This alters the sprite's tint, giving it a ghostly hue. Swizzling can be done with any combination of vector components, so if we wanted to, we could do something like take one of the original channels, like red, and put that single value into each of the R, G, and B channels, giving us a grayscale effect. Or we could put the alpha channel value into each of the channels, giving us an alpha mask effect. The components can be used to store other data as well, not just color components, but we won't do that for today. Anyway, the goal of this swizzle is to make the original sprite change tint, but we could easily remove or change this swizzle if we wanted to. Okay, here the ghost's vertical position is controlled by an input setting, the ghost progress uniform. At 0 progress, the ghost overlaps the original sprite. As the progress value increases, the ghost floats upward, moving halfway up the expanded mesh. This simple vertical drift is a key part of the ghost effect, and the progress input setting is how Godot will animate the effect. To add a blur or pixelated look to the ghost, the shader uses mip-maps. Mip-maps are pre-computed, lower resolution versions of a texture that help make things look better when images are zoomed out or if they're far away from the camera. But we can also use them to create blocky, pixelated, or blurring effects, which is what this shader is doing here. For 2D textures, mip-maps are not automatically turned on, so you need to tell Godot that it should pre-generate the low-res versions. If you're looking at the texture in the inspector, it'll show you how many mip-map versions it has. If it says no mip-maps, you'll need to re-import the texture. To re-import, first open the texture in the File Explorer, then click the Import tab near the scene tree. Then, in the import settings, make sure the Generate Mip-Maps option is checked. Finally, click the Re-import button. Once generated, Godot will list how many mip-maps are available. This example uses 6. Next, the sprite's texture filter should be updated to a mode that supports mipmaps, like nearest mipmap or linear mipmap. Nearest mipmap gives a more blocky, pixelated look. Linear mipmap results in a more smooth, blurry appearance. We could spend an entire video talking about mipmaps and texture filters, but for now, remember that using the nearest filter will give you a more pixelated, granular image, and using linear filtering will do some magic to create new pixel shades that did not originally exist in the original image, giving you a much smoother, blurring effect. I'm showing both examples here just to give you a feeling for how they look different while the images are scaled. Now, with mipmaps available, the shader uses the built-in texture load function to sample the texture at a specific mipmap level. This function works like the texture function, but allows manual control over the blurriness or sharpness of the image. The mipmap level is calculated from the ghost progress value, starting at mipmap level 0 and increasing up to mipmap level 4.5 as the ghost rises. This makes the ghost appear more blurred or pixelated the higher up it floats. For color, the ghost texture is then swizzled, this time using the red channel to create a grayscale version of the original sprite. The brightness is also increased slightly to enhance visibility. The transparency of the ghost is also controlled using the ghost progress uniform. At 0, the ghost is fully opaque, and as the progress reaches up to 1, the ghost becomes more transparent. This gives the effect of a natural fade-out as it rises. This next section fixes an issue I encountered with some textures. It's not always needed, but it's useful to know about if you run into it. Because the mesh was expanded, there's a chance that pixels outside the original texture bounds could be sampled incorrectly. If the original image had edge pixels right up against the border, they can sometimes smear or stretch out visually. To avoid this, these bounds checks verify the UVs. Once UV coordinates fall outside the 0 to 1 range, sampling stops. This prevents the visual artifacts and keeps the ghost effect clean. In the final part of the code, the shader mixes these two layers, the original sprite with its tint adjusted via swizzling, and the grayscale ghost image, fading out and drifting upward, depending on how high the ghost progress is. The result is a cohesive ghost trail that lifts off the sprite and vanishes up into the sky. The ghost progress uniform can be animated using Godot tools like tweens, animation players, or scripted logic. The effect scales naturally over time and can be adapted to different speeds or trigger conditions. It also pairs well with other effects, such as a spooky wobble or the teleport shader shown later in this video. It's a great example of combining vertex manipulation, UV scaling math, and mipmaps to break outside of the limits of a single sprite, while also getting cool blur and fade effects. Okay, let's move on to the next shader. Next up, the teleport dissolve effect shader. This shader pulls together several concepts we've covered earlier in the series, like noise, UV scaling, and step functions. But this time we're using them to create procedural dissolve effects, perfect for making a character zap out of existence or appear out of thin air. Like the last shader, this one lets you control the progress of the effect using a uniform variable that goes from 0 to 1. Here's how it works. The shader begins by generating a 2D noise pattern. This is a simple value noise function, like we saw in the last video, built from dot products and smooth interpolation. It creates a mostly randomized texture across the surface. While basic, this procedural noise serves as a foundation for the dissolve effect. If we wanted more unique noise to get different dissolve effects, we could consider adding a customizable noise as a texture later on. Here, the noise is then multiplied by the y coordinate. This scales the noise vertically, causing it to grow stronger toward the top of the sprite. The result is a directional gradient, where the teleportation begins at the top and travels downward through the object. Then comes the key parts that drive the dissolve behavior, two step functions. The first step compares the noise value at each pixel to the teleportation progress uniform. Pixels where the noise exceeds the current progress are fully removed, simulating the part of the sprite that's already teleported away. The second step creates a narrow band just along the edge of the noise. This produces a beam of color that marks the active teleportation front, adding some visual flair and a sense of motion. That beam can be customized. Here it's multiplied by a color uniform. So whether it's magenta for magic, cyan for sci-fi, or any other aesthetic, the glow can be adjusted to match the game's tone. Finally, the texture's alpha is gradually faded behind the teleportation front. This gives it a soft, smooth appearance, blending the sprite into the background without harsh edges. By adjusting the progress over time, Godot can animate the whole thing using animation players or tweens, or by just driving it with the shader parameters in the inspector if you want something self-contained. You could even combine this teleport shader with the ghost effect from earlier, making a ghost trail linger for a second after a teleport. Or you could even reverse this teleport progress to simulate the sprite teleporting into your world, instead of dissolving out. Small effects, but really versatile, and they look great. I hope you have fun with that one. Okay, next we're jumping even further into procedural territory. Let's make lava blobs. This shader uses random numbers, distance threshold calculations, and soft gradients to simulate floating blobs inside of a lava lamp. Here's how the pieces come together. The shader begins by creating the background. This will represent the clear liquid in the lamp. Instead of a flat color, it uses a horizontal gradient across the x-axis. A mix function blends two color uniforms together based on the UV's distance from the center. This creates the appearance of depth behind the blobs. The background's transparency is then adjusted using a separate background alpha uniform. Then we have the option to turn off the blobs completely. If we do turn them off, the resulting image will still have the customized background color, but no further logic is performed. If the blobs are enabled, then the code continues to create and manage those blobs using several helper functions. A procedural randomness function is defined so the shader can produce consistent but random values. It hashes a 2D vector using a combination of dot, sign, and fract function calls. The result is a pseudo-random value between 0 and 1, based on the x and y coordinates that we send to it. The random seed uniform is also used in the generator to ensure that each instance of the shader produces different results while still remaining consistent internally. This random function is used for the positioning, the speed, and the size of individual blobs later on. Next, an oscillate function will control the vertical movement of the blobs. It returns a sine wave, mapped between 0 and 1, taking time, speed, and a random phase offset as input. It also is given an upper and lower limit to control how far the blobs will move. This gives each blob independent vertical motion, rising and falling continuously, like bubbles in a lava lamp. Now for the main blob creation logic. The shader declares a constant size array to store the blob data. For each of the 6 blobs, the shader assigns 3 values into a vec3. The horizontal position, randomized per blob, the vertical position, animated and randomized using the oscillation and random functions, and the radius or influence factor of the blob, which is also randomized. These values are stored in the vec3 array called blob centers. The shader calculates them in a loop, allowing multiple independent moving blobs to be managed at the same time. Now that we have the blob centers, the shader needs to merge the blobs together to get the distinct lava lamp effect. For each pixel, the shader computes a cumulative influence from all blobs. This is done by measuring the distance between the pixel's UV and each blob center. Each blob's influence is based on its radius, divided by that distance, ensuring a stronger effect closer to the center. In the loop, all blob influences are summed together for the pixel. The result is a smooth distance field, where the influence fades naturally as it gets further away from the blobs. The shader gives even more control over the distance calculation by giving you uniforms to control the blob's scale in either or both the x and y axis. Next, the shader adds colors for the blobs. The classic look of a lava lamp has brighter blobs at the top and cooler, darker blobs at the bottom. So here the blobs are given a vertical color gradient. Using the current y coordinate, the shader blends between 2 customizable color uniforms, one for the upper blobs and one for the lower blobs. This creates a fluid gradient that changes as the blobs move up and down in the lamp. And finally, once the total influence is calculated, and we have the blob color for the current pixel, the shader checks the influence against a threshold. We can configure this blob threshold uniform to make blobs bigger or smaller. Pixels with influence above the threshold are rendered fully as the blob color. Those below the threshold are blended softly between the background and the blob color using a smooth-stepped powered curve, giving the illusion of spherical depth. The result is an organic fade between the blobs and the background, with soft edges that merge naturally as more blobs get closer to each other. And there we go. Lots of uniform settings you can play with to get some interesting patterns. Some of these don't even look like lava lamps and are pretty unique. And finally, our last practice shader. It's a good one, the water wave shader. This effect layers multiple procedural wave functions, calculates a height map, approximates surface normals, and even does some simple lighting tricks using vector math, all inside of a 2D fragment shader. Don't let the code fool you though, there's only a few important components that bring this shader to life, and I'll try to keep it easy on the math. Before we get too far into the shader, first let's look at these define statements. In shaders, define is a preprocessor tool that lets you create shortcuts before the code is compiled. It's useful for two main reasons, readability and portability. For example, this define replaces all instances of tau with the appropriate value, making the math a little bit easier to read. Similarly, this define here allows the shader to use shader toy and other shader language variable names, making it easier to reuse the code across platforms. In many ways, define is similar to using a constant. Both let you assign a value once and reuse it. But define doesn't have a type, and it's handled as a text replacement during compilation. This makes it lightweight, though less strict than type constant values. Defines also let us tweak core settings in one place, like defining the number of waves here. Handy if you want to adjust how many layers of wave motion are combined, without digging through the entire shader. Think of them like global settings or shortcuts that can simplify both coding and experimentation. Okay, let's look at the code in more detail. Each wave in the shader is driven by procedural math. Specifically, trig operations that act like animated sine waves. But instead of a single ripple, the shader blends many waves together. It uses a concept called superposition, where multiple waveforms of different scales and angles are stacked together. Each wave has its own frequency, amplitude, direction, and phase offset. This randomness comes from the golden ratio-based angle, phi, ensuring that waves don't line up in repetitive or symmetric patterns. The result is an intricate interference pattern, ripples of different speeds and sizes interacting over time, giving the appearance of overlapping waves in a pond. The height function accumulates all of these waves into a single floating point value for each pixel, creating a dynamic, time-evolving height map. Think of it like drawing the elevation on a flat surface with using nothing but math. Now that the shader has a height map, the next step is to approximate the surface normals. A surface normal is the direction immediately facing outward from a flat plane. But since this is a 2D shader, it doesn't really have a surface mesh to sample from. It only has our height map. So it uses a technique called finite difference approximation for the current pixel. Imagine comparing the pixel to a point slightly to the right and measuring how much the height changes, and do the same for each of the directions. Those height differences give us a slope of each pixel in x and y. These tiny gradients are treated like a pair of tilted lines, and by taking their cross product, we can reconstruct a 3D normal vector. This gives us something similar to a normal map, except it's calculated entirely from math on the fly, no texture required. It's a powerful trick, dynamic normals from nothing but a height function. So now we know which direction is facing outward for each of these pixels. With the surface normals calculated, lighting becomes possible. The shader uses a directional light vector, like a fake sun above the water, and compares it to the surface normals using a dot product. Dot products are common math tricks useful in shaders, and especially for lighting. They tell us how aligned two vectors are. So when the surface normal points directly at the light source, the result will be bright, while the more it faces away from the light, the darker it becomes. This gives the water a soft dynamic shading as ripples roll across the surface. But there's more. The shader also uses a cross product when building the normal itself. This adds depth by factoring in the perpendicular direction of change, and in one specific condition, when the surface aligns nearly perfectly with the light direction, it creates a sharp specular highlight. This highlight is the bright sparkle or glint you sometimes see on the crest of waves, and enhances the illusion of reflective water. Together, these simple vector math tricks give the appearance of foam, depth, and shine. After the lighting and geometry are figured out, the final pixel color is constructed by blending several components together: the sky, the water, the foam, and the specular values. There's the base texture, the original water image or color tint. On top of that, it blends in a subtle sky tint based on the surface angle, helping simulate light coming from above. If the water is nearly flat and facing up, it appears more reflective and sky-colored. It also adds the highlights for foam, and the sun glints using specular color. These bright spots help sell the wave motion glinting in the sunlight. And finally, the entire output is faded out using a customizable alpha value. This transparency tweak can be used to layer the water over a background, or tune the effect's intensity. Because the whole pipeline is modular, we can tweak the base texture and the lighting colors, or even remove the texture entirely, making this a flexible template for anything from magical fog to sci-fi energy shields. You can easily rework this for lava flows, swampy lowlands, or other fun patterns with a little color tweaking and texture tweaking. And that's a wrap on this shader miniseries. Back in part 1, we started with simple UV scaling, animations and color space tricks, and here we ended with map-enabled textures, lighting-aware effects, and procedurally distorted features, all in 2D, all in Godot. If you followed along, huge congrats! You now have a toolkit of shader techniques to mix, match, and layer your own visual effects together. And honestly, I'm still learning too. Every time I pick apart one of these shaders, I discover something new. If you make something cool with these techniques, please share it in the comments or tag me online, or even post it on GodotShaders.com for others to enjoy. I'd love to see it. Until next time, keep experimenting, keep breaking stuff, and never stop learning. Thank you for watching the Pathfinder's Codex.